Okay, let's go through the Fourier coefficients of this piecewise function. Alright, today we're looking at finding the Fourier coefficients for a specific piecewise function. The function is given by f of t, which is defined in two parts. Its sine of t when t is between 0 and pi, and its minus sine of t when t is between minus pi and 0. We're asked to find the Fourier coefficients, and we have four options here to compare our result against, particularly focusing on what happens when n is even, or odd. So first off, let's clearly state the function again. F of t is sine of t for t between 0 and pi and minus sine of t for t between minus pi and 0. This function is defined over the interval from minus pi to pi. So the total length of this interval, the period t, is 2 pi. The fundamental angular frequency omega 0 is calculated as 2 pi over the period t. In our case, that's 2 pi over 2 pi, which simplifies to just 1. Now before we dive into the calculations, let's analyze the symmetry of the function. This can often simplify our work a lot. We can actually express f of t more simply as the absolute value of sine of t for t in the interval from minus pi to pi. Let's check what happens when we plug in minus t instead of t. F of minus t is the absolute value of sine of minus t. We know that sine of minus t is equal to minus sine of t. So this is the absolute value of minus sine of t. So this is the absolute value of minus sine of t. Minus sine of t is the same as the absolute value of sine of t, which is our original f of t. Since f of minus t equals f of t, the function is even. For an even function like this, the Fourier series has a special property. All the sine terms in the real Fourier series are 0, or in terms of complex coefficients, the b coefficients are 0. This means we only need to worry about the cosine terms or the real part of the complex coefficients. Let's define the Fourier coefficients using the complex series representation. The function f of t can be written as the sum from n equals minus infinity to infinity of cn times e to the power of in omega 0. The formula for the complex coefficient cn is 1 over t times the integral from minus t over 2 to t over 2 of f of t times e to the power of minus in omega 0 t dt. For our function, t is 2 pi and omega 0 is 1, so cn is 1 over 2 pi times the integral from minus e to pe of f of t times e to the power of minus int dt. Because f of t is even as we just found, and e to the power of minus int can be written as cosine of nt minus I times sine of nt, the integrand f of t times e to the power of minus int becomes f of t times cosine of nt minus I times f of t times sine of nt. Since f of t is even f of t times cosine of nt is also even, and since f of t is even f of t times sine of nt is odd, the integral of an odd function over S symmetric interval like minus pi to pi is 0, so the imaginary part of the integral goes away. This simplifies our integral for cn to 1 over 2 pi times the integral from minus pi to pi of f of t times cosine of nt dt. And because f of t times cosine of nt is an even function, we can integrate from 0 to pi and just double the result. So cn is 1 over pi times the integral from 0 to pi of f of t times cosine of nt dt. For the interval from 0 to pi, our function s of t is simply sine of t. So the integral we need to evaluate is 1 over pi times the integral from 0 to pi of sine of t times cosine of nt dt. Okay, let's evaluate this integral. We'll call the integral I, which is the integral from 0 to pi of sine of t times cosine of nt dt. We can use a product to sum trigonometric identity here. Sine of a times cosine of b is equal to 1/2 times the quantity sine of a plus b plus sine of a minus b. Applying this, our integral I becomes the integral from 0 to pi of 1/2 times sine of 1 plus n times t plus sine of n minus n times t dt. We can pull out the 1/2 and also rewrite sine of 1 minus n times t as minus sine of n minus 1 times t. So I is 1/2 times the integral from 0 to pi of sine of n plus 1 times t minus sine of n minus 1 times t dt. We need to be careful here because if n equals 1, the second term becomes sine of 0, which is 0. Let's handle that case separately. Case 1, n equals 1. The integral I becomes the integral from 0 to pi of sine of t times cosine of t times cosine of t tt. We can use the identity sine of 2t equals 2 sine t tt as minus sine of n minus 1 t tt. Or just integrate directly. This is the integral from 0 to pi of 1/2 times sine of 2t dt. The integral of sine of 2t is minus cosine of 2t over 2. So we have 1/2 times minus cosine of 2t over 2 evaluated from 0 to pi. This is minus 1/4 times cosine of 2 pi minus cosine of 0. Cosine of 2 pi is 1 and cosine of 0 is 1. So we have minus 1/4 times 1 minus 1, which is 0. So for n equals 1, the integral is 0. This means c1, the integral is 0. Equals 1 over pi times 0, which is 0. Case 2n is not equal to 1. Now we can integrate the expression we had using the standard integral of sine of ax I is 1/2 times the quantity minus cosine of n plus 1 times t over n plus 1 plus cosine of n minus 1 times t over n minus 1 evaluated from 0 to pi. Let's plug in the limits. I is 1/2 times open bracket minus cosine of n plus 1 times pi over n plus 1 plus cosine of n minus 1 times pi over n minus 1 closed bracket minus open bracket minus open bracket minus open bracket minus cosine of 0 over n plus 1 plus cosine of 0 over n minus 1 closed bracket. We know that cosine of k times pi is equal to minus 1 to the power of k, and cosine of 0 is 1. Also note that minus 1 to the power of n minus 1 is the same as minus 1 to the power of n plus 1. Let's call this value minus 1 to the power of n minus 1. So I is 1/2 times open bracket minus 1 to the power of n plus 1 over n plus 1 plus minus 1 to the power of n minus 1 over n minus 1 to the power of n minus 1 over n minus 1 over n minus 1 over n minus 1 closed bracket minus open bracket minus 1 over n plus 1 over n minus 1 closed bracket. Rearranging terms, we get 1/2 times open bracket minus 1 to the power of n plus 1 times minus 1 over n plus 1 plus 1 over n minus 1 minus minus 1 over n plus 1 plus 1 over n minus 1 closed bracket. This can be factored as 1/2 times the quantity minus 1 to the power of n plus 1 minus 1 times the quantity minus 1 over n plus 1 over n plus 1 minus 1 over n plus 1 over n plus 1 over n minus 1 over n minus 1 over n plus 1 plus 1 over n plus 1 plus 1 over n minus 1 over n minus 1 minus 1 over n minus 1 minus 1 over n minus 1. 1. Now let's combine the terms in the second parenthesis. Minus 1 over n plus 1 over n minus 1 equals minus n minus 1 plus n plus 1 all over n plus 1 all over n plus 1 times n minus 1. This simplifies to 2 over n squared minus 1. So I is 1/2 times the quantity minus 1 to the power of n plus 1 minus 1 times 2 over n squared minus 1. The 1/2 and the 2 cancel out. So the integral I is equal to minus 1 to the power of n plus 1 minus 1 to the power of n plus 1 minus 1 all over n squared minus 1. This is for n not equal to 1. Now let's determine the coefficient Cn based on whether n is odd or even for n not equal to 1. Substitute the integral result back into Cn equals 1 over pi times I. Cn is 1 over pi times the quantity minus 1 to the power of n plus 1 minus 1 all over n squared minus 1. If n is odd and n is not equal to 1, n plus 1 is an even number. So minus 1 to the power of n plus 1 is equal to 1. Cn is 1 over pi times 1 minus 1 over n squared minus 1, which is Cn is 1 over pi times 1 over n squared minus 1, which is 1 over pi times 0 over n squared minus 1. This is 0. Remember we found C1 was also 0, so Cn is 0 for all odd n. If n is even n plus 1 is an odd number, so minus 1 to the power of n plus 1 is equal to minus 1. Cn is 1 over pi times minus 1 over n squared minus 1, which is 1 over pi times minus 2 over n squared minus 1. This gives us Cn equals minus 2 over pi times n squared minus 1. This is for all even n. Okay, let's compare our results for the coefficients with the options given. We found that the complex Fourier coefficients Cn for n greater than 0 are Cn is 0 for odd n, Cn is minus 2 over pi times n squared minus 1 for even n. Let's look at the options provided. A minus 2 over pi n squared minus 1 for even n. This exactly matches our result for even n. B minus 2 over pi n minus 1 for even n. This does not match. The denominator is different. C minus 2 over pi m squared minus 1 for odd n. This does not match. We found Cn is 0 for odd n. D minus 2 over pi n minus 1 for odd n. This does not match. So based on our calculations, the Fourier coefficients Cn for even n match option A. Therefore, the final answer is A.